Yes, this is 300 plus academy. Yes, I am Adeyemi Abiodun. I am the lead tutor with 300plus.com. So, still on the subject matter GCE alternative to practical physics. We're trying to look at a probable question for your exams. Okay, all we do at 300plus.com is exams tutoring because our aim is to ensure that you ace and pass your next exams very well. Okay, let's get right into it. The experiment we have for you today is on mechanics, talking about a meter rule seated comfy on two knife edge A and B. Okay, then a mass is on somewhere mid between A and B, so that the meter rule then depresses, creating a distance D, and of course the vertical height of the meter rule being measured upwards. Okay, if you look at the second paragraph in that question, that we were told to determine the initial pointer position YO when the mass MO is not when the mass M is not being hung on the meter rule. The initial pointer position YO is red. So measuring on figure 1A, the initial pointer position as read here is actually 8.0 centimeter. That uh, I have written on the board already. Okay, that's 8.0. Okay, we were also told um, in Roman figure 1, okay, when the mass M is being hung, we were told to determine the final position of Y, talking about serial number 1 to 5. And when we measured, Y1 falls at 8.30, Y2 falls at 8.60, Y3 falls at 8.70, the fourth falls at 9, and the fifth at 9.0. Take note, what we are measuring here is, okay, we have a knife edge A, a knife edge B, and then we have a meter rule. We have a meter rule being placed on that two knife edge at point A, point B. Then a mass is then hung somewhere in between, so that the meter rule depresses. Then we're trying to measure, we're trying to measure the various heights at that point, the level of depression of the meter rule at that point. So we've been able to get the initial pointer position, YO, initial pointer position, when mass M is not being hung on the meter rule. Okay, now in Roman figure 1, I will say read and record the initial pointer position YO and the final pointer position of Y. These are the final pointer position of Y as seen on figure 1A. And also measure and record the corresponding values of L. Values of L talks about the distance between the two knife edge on which the meter rule is seated. So for various distances between the knife edge given as L, L1, L2, L3, L4, and L5. Take note that for L, we have a scale there, 1 centimeter to rep 10 centimeter. If you look at figure 1B, 1 centimeter is represent 10 centimeters. So we were told to measure and record the corresponding value of L. The corresponding value of L, of course, for L1 it is 5 centimeter, but because we have 1 centimeter to represent 10 centimeters, so it means 5 times 10, and that's why we have 50. For L2, that is actually 6 centimeter. 6 times 10, 60. For L3, that is actually 7. 7 times 10, 70. For L4, that is 8 centimeter. 8 times 10, 80. And for L5, that is actually 9.1. And therefore 9.1 times 10 gives us 91 centimeters. So that ends that. On Roman figure 3, we were told to evaluate D. D talks about Y. Take out the initial pointer position, and that's what gives us D. The initial pointer position is YO. So by the time we now hang mass M, we create a depression. So there is a difference between the initial pointer position YO and the new pointer position. So in this regard, 8.30 take away 8, 0.30. 8.60 take away 8, 0.60. 8.70 take away 8, 0.70. 9.0 take away 8, 1. 9.70 take away 8, 1.70. That is to get values for our D as stated that we should find in Roman figure 3. Also, we were told to evaluate LQ in on Roman figure 3. Yes, L cube in each case. Okay, if my L is 50, so 50 times 50 times 50 gives me 125,000 cm cube. Then 60 times 60 times 60, 60 times 60 times 60 gives me 216,000. 70 times 70 times 70 gives me 343,000. 80 times 80 times 80 gives me 512,000. Then 91 times 91 times 91 gives me 753,571 cm cube. I've been able to carry out that. Okay, on Roman figure 4, I was told to tabulate my readings. That exactly I have done. Okay, on Roman figure 4, I was told to plot a graph of D on the vertical axis against L cube on the horizontal axis. That's Roman figure 5. Yes, plot a graph of D. Graph of D in centimeter against L cube in cm cube on the horizontal axis, and that is what I am going to try to do. So the first thing to do is to write down my, of course, title graph. Graph of D in centimeter. Graph of D in centimeter against L cube in cm cube. Okay, now we already have that written out. Now the next thing we do is, of course, irrespective of what our point is going to be, we want to first of all get our vertical line in place. Take questions seriously, and try to look at all the processes we follow. Recall that your physics practical, very important for you to be able to get an A, or at worst a B in your physics. Okay, avoid broken lines, avoid too thick lines, but let your lines be visible enough, provided that the pencil you are using has a very good lead in it. Okay, this way I've been able to draw for my horizontal axis. Okay, my horizontal axis in this case is going to be L raised to power 3 in cm cube, and my vertical axis in this situation is going to be D in centimeters. So I haven't done that. I'm looking at 0.30 to 1.70. 0.30 to 1.70, and I'm beginning to think, okay, what should I be doing in this case? So I'm thinking, okay, if this is 0, Okay, how about 0 point coming 0.40, 0.80, 1.2, 1.60, 1.70, sorry, 1 point, this is 1.60, then I'm looking at 2.0, 2.00. Okay, if you are, as you are going to be plotting on paper, I would suggest that in this case, 2 centimeter, in the case of this graph, for this centimeter, 2 centimeter represents 0.40 centimeter. So if you're plotting on paper, your 2 centimeter can represent 0.20. If you are plotting on paper, your 2 centimeter can represent 0.20 because of course you have more length when you're plotting on your paper. Okay, that ends that. Now let's look at our L cube. L cube talks from 125 to 700. So I don't want to stress that out. I just want, okay, let this be my 100,000, 200,000, 300,000, 400,000, 500,000, 600,000, 700,000, and of course, although I have my L here in cube, this is my 800,000. Okay, I've been able to do that. So which means on my L cube axis, L cube in cm cube, on that axis, what I have is 2 centimeter to represent 100,000 cm cube. Okay, that way I've been able to get down my scale, and the next thing now is to try to pick my point. Okay, very easy. Does it? Okay, I'm looking at this like, okay, if I look at each hole that I have here, 0.40 divided by 10 is 0.40 divided by 10. That will give me 0.04. Okay, 0.04, because what I need there is I need a 30. So 0.04 times 8 is going to give me 0.032. So this 0.30 should be somewhere just before 8, the end of the 8 hole. So 0.30 and 125,000. This is 110, 120, 125 falls here. So in picking this point, this is going to fall here. So I've been able to pick my first point. Second point, 0.60. If this is 40, then my 60 is going to be in between 40 and 80. So 1, 2, 3, 4, 5. Okay, that's 5. So, and I'm looking at 216, 210, 220. So 216 is somewhere. 216 is somewhere in between here. So if I trace that up, no, it should be here. Yes. Okay, That settles that. Okay, then the next one is 0.70. Okay, if this is 0.60, 0.64, 68, 72 should be here. So just before 0.70 and 343, 310, 320, 330, 340, 343 should just be somewhere immediately after 340. Okay, if I chase that out, no, that should be somewhere here because I have 0.70 before, so that should be somewhere here. If I trace that out, yes, that should be somewhere here. So I've been able to take that. Okay, so the next thing, I have 1. Okay, 80. 1 should be in between. So we got 1 to just the 5th one. That's the 5th one. So 0.81. 1 and 512,000. 512. 510, 512 should be somewhere here. Should be somewhere here. So if I trace that up, I am looking at somewhere here. Yes. Okay, I've been able to take that down. Then lastly, I have 1.70. 1.70. This is 1.60, 1.64, 1.68, 1.70 should be somewhere around here. Okay, 1.70 and 753. 753,710, 20, 30, 40, 50. Somewhere around there. That's where I'm going to have this. So if I trace that up, somewhere here. So I've been able to take that as well together. So having 5 points here, well, I don't have to take all the 5 points together. I don't have to. I'm only going to have to make do with what I have. I'm going to make do with what I have. So that ends that. I've been able to plot my graph. Now, the next thing is I was told to determine the slope S of this graph. For me to determine the slope of this graph, if I try to pick my point from here, it takes only 2. You can see that if I take this, it takes only 2. If I take this, it takes 3. So I'm going to go for the one that picks 3 points, ignoring the remaining 2. So that goes this way. Okay, this is just the point that takes 3 out of the line. So since I want to determine the slope of this graph, I'll try to, I'll go with what I am comfortable with, the kind of triangle I'm comfortable with. I'm comfortable with this, yes. Okay. Can I extend this? Okay, I could just stop here so that I stop on a tick line. Let me get my black marker. Okay, so I'm gonna take that out. This is the line of best fit for me, what I'm comfortable with. Okay, I'm comfortable with this. So what's going to happen here is that what I have here is my change in D centimeter, and what I have here is my change in L cube, in cm cube. That's what I have. Now the next thing is for me to pick out my extrapolation, my extrapolated line. Okay, this stops here. So I can just get that out. Remember, when you're doing this, you make use of your ruler. Okay, I've been able to do that. Okay, and for the x, you trace that out as well. Okay, I've been able to get that, and for my x here, okay, it goes like this, and for my y, it stops 0.40. Okay, it goes this way. Okay, so with what I have, I should be able to, get through with my slope. Talking about question Roman figure 6, as I have in that question, I was told to determine the slope of the graph. The slope x of this graph is going to be changed in d centimeter. Change in d centimeter, of course, that's the vertical axis, divided by the change in L cube in cm cube. Okay, what I have here is this is 1.20 and 0.40. 1.20, take out 0.40 in centimeters. And for the L cube, this falls on, this is 100, 110, 120, 130, 140, 150, 160, 170. Okay, I have 170,000 in cm cube. Take out. Now I have 600 here. 610, 20, 30. 630,000. So this is what I want to do with. This will give me 0.80 centimeter. And of course, 630 take away 630,000, take away 170,000. 630 take away 170,000. That's going to give me 460,000 cm cube. Of course, this takes out this, so 0.80 divided by 460,000. I'm going to get 0. I'm going to get 0. That's going to give me 0.0000001. Yes, 17. So that what that means is 1, 2, 3, 4, 5, 6. Yes. So I can put this way. This will be in per centimeter square, because of course 1 centimeter are taken out 1 centimeter. So this is what I have, or I leave it as 1.7 times 10 raised to power minus 6 centimeter per centimeter square, and I'll be correct. So that is the value of my slope as I was told to express in question 6. For question 7, I was told to express to evaluate y. For question 7, I was told to evaluate y. Y is actually given as 2.5 times 10 raised to power minus 13 divided by my slope. So of course, this will mean 2.5 times 10 raised to power minus 13 divided by the slope. In this case is 1.7 times 10 raised to power minus 6. 2.5 divided by 1.7. 2.5 divided by 1.7. That is 1.47. 1.47 times 10 raised to power minus 13 minus 6. That's going to give me 10 raised to power. That's going to give me 10 raised to power minus 7. Yes, 10 raised to power minus 7. Take notes. This has no unit. This is in per centimeter square. So Being that it has a negative index as a denominator, now that becomes centimeter square. Take note of the unit, not writing a unit for this. What it now means is that you're missing out on valuable marks. So this is for question 6, and this here is for question 7. This is for question 7, where we were told to express y, or evaluate y equals to 2.5 times 10 raised to the power minus 13 divided by the slope, which is in per centimeter square. So since the slope is the denominator, no wonder this per centimeter square becomes centimeter square. So that ends question 7. On question 8, we were told to state 2 precautions that are necessary to ensure accurate results when performing this experiment. Okay, so that ends question 8. Okay, ends question 7. For question VII 8, we were told to state 2 precautions necessary to ensure accurate results when performing this experiment. Okay, you recall that there was a mass hanging somewhere around the midpoint of the meter rule. The first precaution is to ensure that that mass is not resting on the table. Yes, it must not rest on the table. Also, in taking our readings on the vertical scale and on the meter rule, we must avoid parallax error. Also, we must always note and correct zero error on any instrument we are using. In this case, our instrument is the meter rule, so we must correct zero error. Okay, that ends that. On question B Roman figure 1, we were told to state the conditions under which a number of parallel coplanar forces will be in equilibrium. We're looking at conditions for equilibrium under the action of forces that are parallel acting on a plane. Okay, the conditions falls into 2 categories. First, we look at the forces, and secondly, we look at the moment. The very first conditions for us to have equilibrium is that the upward forces must be equal to the downward forces. That is, the algebraic sum of all of the forces must be equal to 0. And the second condition is based on the principle of moment. Okay, we all know that moment is the product of force and perpendicular distance. The sum of the clockwise moment about the point must be equal to the sum of the anti-clockwise moment about any other point. That is, the algebraic sum of your moment must be equal to 0. For more understanding on that, you should look at your equilibrium in physics. Okay, that ends that. On B2, we have a question. We're told to, in the diagram above, that the point G is the center of gravity, that we should calculate the tension. Of course, we can use this condition 1 for equilibrium to actually determine what our answer will be in question 2. Since between T2 and the G we don't have any distance, and between T1 and the center of gravity G we don't also have any distance, we can just use the forces. If you look at T1 and T2 are acting upward. So that's what I mean by upward forces equals to the downward forces at G. So this is acting downward. Okay, so my T1 from that question is 50 plus T2 equals to 120 Newton acting downward. Therefore, my T2 equals to 120, take out 50, and therefore my T2 is actually 70 Newton. And with that, we've been able to answer all of the questions related to this experiment. Take it serious, it's a probable question. Okay, with that, we've come to the end of this. Don't forget, you can comment, you can ask questions. Also ensure to like our videos, tell us what you feel. Also do remember to subscribe and give us a thumbs up. And as well, remember to turn on the notification bell so that as we begin to upload our videos, because we're not started yet, we're just about to start everything that relates to your next exam: UTME, WAEC, SAT, TOEFL, IELTS, and all of GMAT, GRE Math. All of this we have in stock, and that's why I'm saying we've not even started. We're just about to get started, so that when we upload any of our lecture videos, you can get notified. Also, do not forget to check us out on our website at 300 plus academy.com, where you can link up with your peers writing similar exams, and also you can anonymously ask us questions in our DM there. Thank you from myself and the team at 300 plus academy. We'll say bye for now.